Okay, so Hess Law calculations are about determining the change in heat when we have a chemical reaction. And so we have to remember simply that when we form bonds, those chemicals decrease in energy, and that energy is released in heat. And we represent that with a negative delta H. So heat is being released from the chemicals into the environment, which causes a temperature increase. And the other way, when we break a bond and these things come apart, they're no longer together. That requires energy to be put in. So we need to increase the energy of the system of those chemicals. And when we increase that energy of them, that's positive delta H. And that heat is taken from the surroundings, from the environment, which is related to a drop in temperature. Okay, and so when we look at overall reactions, what are chemical reactions? Well, chemical reactions involve making and breaking different bonds. So they'll involve losing energy from the chemicals and gaining them. So overall, we need to see what does the whole chemical reaction do, and this is what the heat of reaction is, right? Is the whole reaction overall going to be more a negative heat change or a positive heat change? And so how can we calculate that? Well, before we go ahead and calculate that, we need to look at two different types of reactions that are generally asked. And so the first would be just called heat of reaction, and so we'd have maybe two molecules reacting to form two different molecules. And the second is a bit more specific type of reaction, which would be some molecule, which I'll call X, reacting with oxygen to form carbon dioxide and water. And so these are called combustion reactions. So the heat of this reaction would be called a heat of combustion. Okay, and so the best way to demonstrate this is to look at an example. So here's an example here. We have a chemical reaction here that's called steam reformation, right? And so we have methane and water producing carbon dioxide and hydrogen here. And so this process is for producing hydrogen for use as like a gas. But anyway, let's look at the information we're given here and see how can we use this to calculate the overall heat of reaction. Well, what information are we given? So we're given the heats of formation of methane, steam, which is just water, and carbon monoxide as all these values here. And they give us the balanced chemical equation. So what can we do? Well, what information do we have really? We have the heats of formation information. And so what we can do is we can write out the equations for forming these chemicals first. So let's just do that. Step one, we're going to do that. So I'm going to write numbers for the equations 1, 2, and 3. And I'll start with methane. So if we're to form methane, if we're to form CH4, what do we need to form that? Well, it's very obvious we need one carbon. And what else do we need? We need hydrogen. And whenever we're forming these, we want to form it from its constituents, what it's made up of, in their kind of natural state. And so the carbon atom just exists as an atom. But when we look at hydrogen, it's usually existing as the diatomic molecule, H2, similar to O2 and N2. So those ones usually exist as pairs, not as singular atoms. And so we can describe this as H2, and how many do we need? We need 2 to get those 4 hydrogens. So how would we form methane? If we had a carbon and we had 2 hydrogen molecules, that would do the trick. We have CH4. And so what was the heat? The heat change related to that was negative 74.6. Why is it negative? Because bonds are being formed. And remember, forming a bond releases energy. And breaking a bond requires you to put energy in. Okay, and now next equation, what are we looking at? We're looking at steam, or just simply water. And so if we're to produce water, what molecules do we need? I think it's fairly obvious again. We have our oxygen, and for hydrogen, we would just have one H2 to get H2O. And what was the change there? It was negative 242. And next, if we look at the carbon monoxide, again, how would we produce carbon monoxide? We'd have one carbon, one oxygen, easy stuff, negative 111, they told us. Okay, so all we've done here is we've written out the chemical equations to form these molecules, and we've written down again the heats of formation next to them. And so how can we use this information? Well, this is the information that they want us to start with, and we need to get to this end equation up here. We need to get to this reaction, because we don't want to end up with the heats of formation. That's what they've told us. We want to end up with the heat of this overall reaction. And so how can we do that? Well, we can look at these equations one by one, and we can see how can we get all of our compounds here, all of these molecules, on the correct side of this equation. And I'll show you what that means. So let's look at equation 1. We have methane here, but methane here is on the right hand side of this equation. Up here, is it on the right or the left hand side? So it's on the left. So we don't want this to be on the right hand side. It's on the incorrect side here. So what could we do to this equation? Well, we could make it go backwards. And I'm going to represent that by writing REV in brackets for reverse. I'm going to reverse this equation. And I'll look as well and see how many methanes is there. So in this case, there's just one, and there's one here. So I don't need to multiply this equation by anything. I'm happy just to reverse it, and that should be okay. So let's look at water then, the next equation, equation 2 here. Is water on the correct side? Well, down here, water's being formed. Down here, water's being broken. It's on the left side of the reaction. Water's not being formed. So we would need to do the same thing here. We would need to reverse it. And there's just one water here and one water here, so we don't need to multiply by anything. Next, we look at the carbon monoxide. And so the carbon monoxide, is that on the correct side? Well, here it's being formed, here it's being formed. It's on the right-hand side in both cases, so it's all good. We don't need to do anything. And there's one here and one here, so we don't need to multiply this equation by anything. So this equation's all good. We don't need to do anything. So after I manipulate my equations, I'm going to rewrite them. So I have my methane up here, and what do we say we're going to do to it? We're going to reverse it. And so if we reverse it, what would it look like? It would look like CH4 going back to carbon and 2 hydrogens, okay? 2 hydrogen molecules, rather. And so what happens to this value? Well, if we had a negative delta H value for forming methane, aren't we therefore going to have a positive value for breaking it up? And so we have to, when we reverse an equation, we change a negative value into a positive one, and vice versa. If it was a positive value, you would be changing it to a negative one. And so let's look at the next equation, because that's done. How would we reverse the second one? Equation 2. Well, we'd have H2O going to a hydrogen and an oxygen. And so what would happen to our value? It's negative, and that would become positive, because we were forming a bond in this case, and in this case, we're breaking it. And then lastly there, let's look at equation 3. And so here, we didn't need to do anything, so it's just how it is. So I can just rewrite it so we have it very clearly down here. But it's just the same. Nothing happened to this one. And so where do we go from here? Well, the reason we just manipulated these equations, such as reversing them as we saw, is because we wanted to get our groups that they gave us, our methane, our steam, and our carbon dioxide, on the correct sides. And what was the purpose of that? Well, we should now be able to add up these equations as such, so that we get this equation over here. And what's the purpose of doing that? Well, if we also add these heat changes all together should tell us the overall heat change of this reaction, the overall delta H of this reaction here. And so let's have a go. So if we look here first, how can we add up chemical equations, right? Well, how we can add chemical equations is if there's anything common on both sides of the arrows, we can cancel them out. That's where we can start. So let's take a look and see, is there anything on both sides that's common? And well, if we look, we can see clearly there's a carbon here and a carbon here. There's an oxygen here and an oxygen here. And what else is there? Anything else that cancels out? Where we got a CH4, a H2O, anything here? No. So it seems like that's all that cancels out. So now that we know what cancels out, we can simply add everything together that's on either side of the arrows. So on the left side, let's take the left side first. What do we have? Well, left over, we have a CH4 and we have a H2O. And on the right-hand side of the arrows, what do we have? Well, we have a 2H2 and a H2, so we'd have 3H2, and we have a carbon monoxide. So our carbon monoxide and 3H2. And, okay, what did I say? When we add those all together, we should get the equation that we were looking for. Did we get that? CH4 plus H2O to carbon monoxide and 3H2. Indeed, we did. So that's perfect. And so if we did those steps correctly to get this, we should know that all these heat changes together should also give us the overall heat change for this reaction. And so if we just calculate that, we should get 74.6 plus 242 minus 111, if we use our calculator, should be plus 205.6. And remembering our units there of heat changes in reactions is kilojoules per mole. Okay. Okay, and so moving on to the next example, the second type of equation we were talking about was a combustion reaction. And so let's look at this question. The heats of formation of propane, carbon dioxide, and water are so and so respectively. Write a balanced equation for the combustion of propane in plentiful oxygen supply and use the data provided to calculate the heat of combustion. And so when we look at this, it's really nothing too different. We just need to work out what is this chemical reaction. So it's still a chemical reaction. This is still a type of heat of reaction. But more specifically, this is a combustion reaction. And so this is called heat of combustion. So if we look at the reaction we're trying to build here, we're trying to build the combustion of propane. And so when we think about propane, prop means 3 carbons and ane an alkane. So if we think about what's the formula of propane, if we don't just remember, we can draw it out. And so we have 3 carbons. And how many hydrogens? We'd have 1, 2, 3, 4, 5, 6, 7, 8 going around. If you fill in all your hydrogens there, you'd see there's 8. And so we can then say that formula of propane is C3H8. And so what is a combustion reaction? I said a combustion reaction is when we have something, in this case it's propane, with oxygen, and we're getting carbon dioxide and water. And so the first step we have to look at is this balanced? And so in this case it's not balanced. So how do we go about balancing this? So to balance this, we want to look at how many of each atom we have on each side to start with. So we can draw a small table here, and we'll put this is the left hand side, this is the right hand side, and what chemicals do we have? So what atoms? We have carbon, we have hydrogens, and we have oxygens. Yeah, that's all. So start with our carbons. We have 3 on the left and we have 1 on the right. Our hydrogens, we have 8 on the left and we have 2 on the right. And our oxygens, we have 2 on the left, and we have 2 here and 1 here is 3 on the right. And so, start again with the carbons. How are we going to balance this? Well, we can put a 3 in front of this carbon dioxide to make 3 carbons on the right. So now that's balanced. Let's look at the hydrogens. We have 8 here and 2 here. How can we balance that? We could put a 4 in front of this H2O, and that will give us 8 on the right hand side, and so now that's balanced. But if we look at our oxygens here, how does that affect our oxygen? So we now have 3 times 2 is 6 oxygens here, plus 4 oxygens here. So we have actually 10 oxygens here. And how are we going to balance that? We have 10 on this side and 2 on this side. And so what can we put here to get 10? We can put a 5 in front of this O2 here, and that gives us a balanced equation. So now we've completed the balanced equation for the combustion of propane.
So now that we've figured out our chemical reaction, our balanced equation, now it's simply the same steps as in the previous example. So we need to take these heats of formation and see how can we manipulate those equations to build our equation up here and add those heat changes together. And so let's look at, again, the heats of formation we're told. So if we talk about propane first, so how would we form, and I'll label this equation 1, how would we form C3H8? And so we can do that with 3 carbon atoms and with 4 hydrogen molecules there, right? And equation 2, what's the second molecule we have there? Carbon dioxide. So forming carbon dioxide, we would have carbon dioxide on the right-hand side. And what forms carbon dioxide? Well, we'd have 1 carbon atom, and we'd have 1 oxygen molecule, and there's our carbon dioxide. Oh, and let me write the heats for this. So minus 104.7, and here we have minus 393.5. And then lastly, what's the last molecule they tell us the heat change for? It's formation, and that's water. So forming water, or H2O, how would we form that? We did that in the last example. We have an oxygen molecule and a hydrogen molecule. Very simple. And what is the heat change there? Negative 285.8. Okay, so we have our equations here and our numbers. And so how do we manipulate these to look like our equation up here? And so let's take our first one. What's the first molecule we're interested in? Was propane. Is propane on the correct side in this equation? Well, it's on the right hand side here, and in the equation we want to build, it's on the left. So what do we need to do? We need to reverse this equation. Do we need to multiply it? Nope, because we have one propane and one propane, so that's fine. Let's look at the next equation where we have CO2. Is CO2 on the correct side? It's on the right hand side here and the right hand side here, so it is on the correct side. But if we look at our equation here, there's a 3 in front of our CO2. We need 3 molecules of CO2 in this balanced equation. And here, we just have 1. So what we need to do to our equation now is we need to multiply the whole equation by 3. Looking to the next equation then, we have H2O. Is H2O on the correct side? Well, here it's on the right hand side. In the equation we want to build, it's on the right hand side. So that's all good. But we need 4 H2Os. And in our equation, we just have 1. So we're going to multiply our whole equation by 4. So I'll draw a line here, and we need to perform all of these operations on our equations and see what we end up. So let's go for equation 1. We said we need to reverse it. So if we reverse it, we end up with C3H8 going to 3 carbons and 4 hydrogen molecules. And when we reverse the equation, we reverse the number in that the negative becomes positive. And so we would have positive 104.7. Equation 2, what operation did we have to do? We said we have to multiply by 3 because we had 1 carbon dioxide in our equation, and then the equation we want, we have 3. And so if we multiply everything in this equation by 3, we have 3C plus 3O2 going to 3CO2. And what do we need to do with our number now? Well, we need to multiply that. So now that we've figured out our chemical reaction, our balanced equation, now it's simply the same steps as in the previous example. So we need to take these heats of formation and see how can we manipulate those equations to build our equation up here and add those heat changes together. And so let's look at, again, the heats of formation we're told. So if we talk about propane first, so how would we form, and I'll label this equation 1, how would we form C3H8? And so we can do that with 3 carbon atoms and with 4 hydrogen molecules there, right? And equation 2, what's the second molecule we have there? Carbon dioxide. So forming carbon dioxide, we would have carbon dioxide on the right-hand side. And what forms carbon dioxide? Well, we'd have 1 carbon atom, and we'd have 1 oxygen molecule, and there's our carbon dioxide. Oh, and let me write the heats for this. So minus 104.7, and here we have minus 393.5. And then lastly, what's the last molecule they tell us the heat change for? It's formation, and that's water. So forming water, or H2O, how would we form that? We did that in the last example. We have an oxygen molecule and a hydrogen molecule. Very simple. And what is the heat change there? Negative 285.8. Okay, so we have our equations here and our numbers. And so how do we manipulate these to look like our equation up here? And so let's take our first one. What's the first molecule we're interested in? Was propane. Is propane on the correct side in this equation? Well, it's on the right-hand side here, and in the equation we want to build, it's on the left. So what do we need to do? We need to reverse this equation. Do we need to multiply it? Nope, because we have 1 propane and 1 propane, so that's fine. Let's look at the next equation where we have CO2. Is CO2 on the correct side? It's on the right-hand side here and the right-hand side here, so it is on the correct side. But if we look at our equation here, there's a 3 in front of our CO2. We need 3 molecules of CO2 in this balanced equation. And here, we just have 1. So what we need to do to our equation now is we need to multiply the whole equation by 3. Looking to the next equation then, we have H2O. Is H2O on the correct side? Well, here it's on the right-hand side. In the equation we want to build, it's on the right-hand side. So that's all good. But we need 4 H2Os. And in our equation, we just have 1. So we're going to multiply our whole equation by 4. So I'll draw a line here, and we need to perform all of these operations on our equations and see what we end up. So let's go for equation 1. We said we need to reverse it. So if we reverse it, we end up with C3H8 going to 3 carbons and 4 hydrogen molecules. And when we reverse the equation, we reverse the number in that the negative becomes positive. And so we would have positive 104.7. Equation 2, what operation did we have to do? We said we have to multiply by 3 because we had 1 carbon dioxide in our equation, and then the equation we want, we have 3. And so if we multiply everything in this equation by 3, we have 3C plus 3O2 going to 3CO2. And what do we need to do with our number now? Well, we need to multiply that by 3 also. And so if we grab a calculator and we go negative 393.5 times 3, we would end up with negative 1,180.5. So everything got multiplied by 3, including the heat change. For equation 3 here, when we multiply everything by 4, we should have, oh, well, first of all, I represented this O atom just by atom by itself, but as I said earlier, we usually represent it as O2, but how can we describe just a single one? We can describe that as a half an O2 molecule. Why do I say we don't just leave it as O? Because when we're multiplying this by 4, we'll actually see it's easier to represent this as 2O2 than as 4O. Because remember we said oxygen usually exists as an O2 molecule. So just to clear that up. So when we get a half O2, which is just an oxygen atom, and we multiply by 4, we end up with 2O2. And what about the H2? We have 4H2, and we'd have 4H2O. And for a heat change, we would have this value multiplied by 4 as well. And so when we get negative 285.8 multiplied by 4, if we pop that in our calculator, we get negative 1143.2.
So after having manipulated these equations to attempt to form this equation above, we need to add everything together to see if we have indeed done that correctly. And so let's look at both sides of the reaction arrows on all the equations, and let's see if anything cancels out on both sides. So we can cancel out this 3C and this 3C here. We can cancel out this 4H2 and this 4H2 there. And is there anything else cancels out? Anything else that's on both sides? It seems like no. So I think we can try and go ahead and add up the rest. So on the left hand side there, we have a C3H8. And we have 3O2 and 2O2 is 5O2. And then on the right hand side, we have, seems like 3 carbon dioxide and 4 H2O. Is that the equation we were trying to build? Indeed it is. and we sorted it up there. So therefore our heat values, when we add all these heat changes together as well, should give us the heat change for this reaction up here. So let's go ahead and do that. If we add 104.7 and negative 1180.5 and negative 1143.2, we should get a total there of negative 2219. And remembering the units, kilojoules per mole. Perfect.